All right, today we're going to tackle one of the absolute biggest challenges in AI. It's this quest to find the perfect balance. And it's a problem that, funnily enough, borrows its name from a classic fairy tale. See, getting this wrong can have some pretty major consequences. So let's dive into AI's Goldilocks problem. I know what you're thinking. What could machine learning possibly have to do with a story about a little girl and three bears? It sounds kind of crazy, right? But believe it or not, this analogy perfectly captures a crucial balancing act that's right at the heart of building AI. And that's exactly where we get this idea of the Goldilocks problem. Just like Goldilocks didn't want her porridge too hot or too cold, or her bed too hard or too soft, well, an AI model can't be too simple or too complex. It has to be just right. This quote from Danny Liu just hits the nail on the head. It perfectly sums up the two extremes we're trying to avoid. A model that's too simple, it's basically useless. But here's the tricky part. One that's too complex can look brilliant, when in reality, it's just memorized the answers to the test instead of actually learning anything. Let's break this down with a quick analogy that'll make it super clear. So an underfitting model, the one that's too simple, is like a student who just skims the chapter summary a minute before a huge exam. They totally miss the key details, and of course they bomb the test. Then you've got the overfitting model, the one that's too complex. This is the student who memorizes every single practice question, word for word. They look like a genius, but the moment the real exam asks the same concepts in a slightly different way, they completely fall apart because they've never actually understood the material. See? Both students fail, just for totally different reasons. And here's what that actually looks like when we're talking about data. Look at the left. That's underfitting. The model is just a straight line, and it's completely missing the obvious pattern in the dots. It's way too simple. Now look all the way to the right. That's overfitting. That chaotic line is trying so hard that it hits every single data point, memorizing all the random noise right along with the actual signal. That sweet spot, it's right there in the middle, the curve that nicely captures the underlying trend without freaking out over every little blip. That's our just right. So why does this even happen? What's going on under the hood? Well, the technical reasons behind this whole Goldilocks problem really come down to two key ingredients, something called bias and something called variance. If you can get your head around these two concepts, you've cracked the code. Okay, first up, bias. The easiest way to think about bias is as a model's stubbornness. It's the mistake you make because your starting assumptions are just way too simple. A model with high bias is going to miss the target again and again and again, simply because it's fundamentally incapable of seeing the real complexity in the data. This is what causes underfitting. For instance, imagine trying to predict house prices using just one single factor, square footage, that's it. You're going to be systematically wrong, right? Because you're ignoring all this other crucial stuff like the neighborhood, the age of the house, how many bedrooms it has. Your model is just too simple. That, right there, is high bias in action. Now, on the complete flip side, you have variance. If bias is stubbornness, variance is more like jumpiness or nervousness. It's the error you get when a model is way too sensitive to the specific data it was trained on. A high-variance model doesn't just learn the important patterns, it learns every single random bit of noise, too. And this is what causes overfitting. A classic example of this is a decision tree model, where you don't give it any limits. It'll just keep splitting and creating new rules until it has a perfect explanation for every single house in your original data. And it'll get a perfect score. But, and this is a huge but, the moment you show it a new house it's never seen before, its predictions are going to be all over the map. Why? Because it memorized the noise, it didn't learn the principles. This table here really lays out the whole dilemma, but I want you to focus on one row in particular, training error. Notice that for high variance, the overfitting model, the training error is low. This is super deceptive because it makes the model look fantastic on the data it was trained on. But here's the punchline. Look at the test error. Both high bias and high variance models fail miserably when it really matters, on new data they've never seen before. This is so important. A low training error does not mean you have a good model. So this constant tension, this push and pull between keeping it simple and making it complex, brings us right to the heart of the matter. It's what data scientists call the great tradeoff. You can't just wish both of these problems away. And here's the real challenge. Bias and variance are basically two ends of a seesaw. When you push one down, the other one almost always goes up. So if you make your model more complex to try and reduce that stubborn bias, you run the risk of cranking up its jumpy variance. And if you simplify your model to reduce the variance, you're probably going to introduce more bias. You're always balancing.
All right, this U-shaped curve you're looking at, this is the central image for this whole explainer. On the far left, where model complexity is low, you've got high bias. That's the underfitting zone. On the far right, where complexity is super high, you've got high variance. That's the overfitting zone. Our entire goal, the whole game, is to find that sweet spot right at the bottom of the U. That's where the total error is as low as it can possibly be. That's our just right model.
And look, this isn't just a nice idea. It's literally baked into the mathematics of machine learning. A model's total error is a sum of three things. It's bias squared, it's variance, and something called irreducible error. And that last part is just what it sounds like. It's the random, unavoidable noise in any dataset that no model, no matter how perfect, can ever get rid of.
Okay, so if we're stuck in this never-ending trade-off, how do we actually find that sweet spot at the bottom of the curve? Well, thankfully, data scientists have developed a kind of recipe for finding that just right balance.
It really boils down to three main strategies. First, you can just directly fiddle with the model's complexity, tuning its settings to be more powerful or less powerful. Second, you can add more training data. This is a fantastic weapon against high variance, because the more examples a model sees, the better it gets at telling the difference between the real signal and the random noise. And third, you can use a really powerful technique called regularization. So what on earth is regularization? Well, in the simplest terms, think of it as a penalty for getting too complex. It's like putting a leash on the model during training. It adds a cost for complexity, which discourages it from getting too wild and memorizing all the noise. Its entire purpose is to make the model perform better on new, unseen data. And this image right here shows you the power of it perfectly. On the right, you've got that overfit model zigzagging all over the place. On the left, it's too simple, it's underfitting. But look at the center. With just the right amount of regularization, that penalty for complexity, we get that beautiful, balanced curve. It literally pulls the model back from the brink of overfitting and guides it towards that just right state. Okay, so this is a fascinating technical puzzle. I get it. But why should you actually care about any of this? Because, and this is the key, getting this balance wrong has serious, high-stakes consequences out in the real world. I mean, think about medical diagnoses. A high bias, underfitting model might be too simple to catch the subtle signs of a rare disease. But a high variance, overfitting model might raise a false alarm over a tiny, meaningless blip in a patient's lab results. Same for fraud detection. You either miss the sophisticated criminals or you end up flagging innocent people's accounts. Even your Netflix recommendations depend on getting this balance just right, so you get new suggestions instead of just the same movies over and over. So at the end of the day, the real art of machine learning isn't just about building the biggest, most powerful model you can. It's about skillfully managing this trade-off. It's about building models that aren't just accurate on paper, but are genuinely reliable and robust when they face the messy real world. And that sweet spot is a moving target. It changes with every new problem and every new data set. And all of this leaves us with one final and maybe even more important question. We've spent all this time talking about how to build a just right model. But what happens when the data we feed it, the data that's supposed to reflect our world, isn't just right to begin with? Well, that's a whole other can of worms. Thanks for joining me.